Started.
Yeah, we were waiting for you. There we go. This session is being broadcast on Zoom. It's also going to be uploaded to YouTube. So if you're a note taker, you really don't need to take notes because you can sit back at home and watch at your leisure anytime. So soon, it should be uploaded within the next day or so to YouTube, and you'll probably be able to find it for if you Google Ivins Geology, it should come up and you'll be able to see the presentation. I want to thank the city of Ivins for letting me come here and use this facility. It's an awesome building and it's seamless audiovisual. I'm going to knock on wood because you walk in, you AirPlay your phone or whatever device you have, and the audio and visual just come on automatically, which is great. So I want to thank them because it's a great facility. All right. So what are we looking at tonight? The geology of Arches National Park. And I don't know if you guys know my name. My name is Marc. And it's Marc with a C. And, you know, I've had to deal with this my entire life. I always have to say Marc with a C. It's kind of like I've gotten into a habit. I don't know why my parents did this. But I went into a coffee shop the other day, and the barista asked me what my name was, and I said my name was Marc with a C. And I went up to get my cup, and that's what it said, Marc with a C. So, so anyway, I think C is for curse. It's the curse of Marc. Okay, so we all know we're Arches National Park. How many people here have been to Arches National Park? Wow, that's great. Well, I hope you walk away with some new information to give you a greater appreciation for it tonight. So here we are, and it's about 250 miles as the crow flies, and about another 100 miles in addition to that if you go up I-15 to 70 and on down 191 to Arches. Okay, so what are we going to cover tonight? It's a very aggressive agenda. I was told by some of my colleagues you'll never do it, so I'm going to do it. We're going to talk a little bit about the plate tectonic history of the United States, of the Southwest US. You're all familiar with plate tectonics, right? Yeah. And then I'll talk a little bit about how Arches compares with our area in Washington County, just to give you a feel for how the geology changes in that 250-mile stretch of territory. And I'll talk about the paleogeographic foundation of Arches. In other words, what did the paleogeography look like? What did it look like during about 300 million years ago during Pennsylvanian time? And I'll talk about halokinesis. How many people have heard of halokinesis? Yes, two. It's awesome. It's salt tectonics. It's how salt moves. We have plate tectonics, how the plates move around on the surface of the planet, right? Well, salt moves too, and it affects the rocks overlying it. How arches form, salt mining. Anybody know about the salt mines, Intrepid Potash, the mines out in the Moab area? And then we'll talk about petroleum occurrences in the basin. We have one geologist here that worked, two geologists, that's right, two geologists that work in the oil industry. So we'll talk a little bit about that. Okay, let's talk about the plate tectonic history. This is an observation map of the world, and this is earthquakes of the greater magnitude of 4 from 1960 to 2000, active volcanoes in the last 10,000 years, and mountains that are actively uplifting. And what you see here are these divergent arrows. Okay, those divergent arrows are talking about or pointing out a divergent plate boundary. This is basically a mountain chain that stretches within the ocean basin, has about 5,000 feet of relief on it, and oceanic crust is being created along those ridges, okay? And it's pushing the continents apart as it's being created, okay? We also see convergent boundaries where the plates are coming together right here. So one plate is diving down below the other, the oceanic crust is melting, and eventually it comes up to the surface in a series of volcanoes or other types of volcanic features. Okay, So let's talk about this area right here in the southwest portion of the US. So our plate tectonic history in the last 100 million years or so, we had an early episode of compression from the Farallon plate diving down below the North American continent, and it buckled the Earth's crust into a series of folds. Hey, Sammy. And then we had a later period of extension from about 25 million years or so to present. And that slide is not. There you go. So our area right here looks like this. A lot of sedimentary rocks that was intruded, but starting about 25 to maybe 27 million years ago, with a bunch of material that came up once the crust started to extend. It allowed cracks to reach those magma chambers that were deep-seated and allowed that material to come up close to the surface or on the surface. Okay, so this is a model, and it's just a very short animation. Moab sits right here. Okay, this is where Arches resides on the eastern side of the state. This is a mountain chain. This is one of those spreading centers, a divergent plate boundary. Okay, I'm going to set it in motion in a second here. The Farallon plate is diving down below the North American continent. So this is about halfway through the compression period. You can see how Nevada is skinny. That's due to the compression. So let's watch and see what happens here. So as that plate dives down below, that mountain chain is bumping up against the North American continent, and it stalls. And you get differential spreading to the northwest, and it starts to extend the crust, opening up the basin and range, and ultimately the uplift of the Colorado Plateau and the creation of the San Andreas Fault System. That makes sense to everybody? So it's compression and then extension. During compression, we created all of these folds up here. Anybody been to the San Rafael swell? Yeah, it's swell. Has anybody ever seen the Virgin Anticline? Yeah, you've all driven to Zion National Park, right? You drove right through it. It's an amazing feature. All right. So all of the folds are asymmetric because all the compression was from the west. So if someone's pushing me on this shoulder, I'm leaning over to one side, right? Well, the same thing happened in the folding process. So the folds are asymmetric, leaning toward the east. Okay, during extension, during this period here, all that magma that was parked below us right here as we sit was released when fractures were opened up during the extension process. And what happened is that we created these features here called laccoliths. The Pine Valley Mountains, sitting right here, is said to be the largest laccolith on the planet that we know of. So yeah, very interesting. So all of these features here are laccoliths: Navajo Mountain, the Henry Mountains, the Bajos, and La Salle. Ah, laccolith is a feature. It's like a volcano wannabe. Never made it to the surface. Okay, it reaches a zone of weakness, and it spreads out along a zone of weakness, a bedding plane, or in the case of the Pine Valley laccolith, it might have hit a cavern system in the Claron Formation and jacked up the entire sequence of rocks about 500 to 600 feet. Yes?
I always wondered, Pine Valley Mountain, what was its maximum altitude?
Thank you. The maximum uplift? They're thinking about probably about 1,200 feet or so of uplift, of all the material lifted up above it, and then it was stripped off through erosion.
So we're not seeing the entire mountain?
No, and a lot of it's in the subsurface as well. If you look at the ages of those laccoliths, they're somewhere on the order, they're less than 30 million years old, but they fall in the range of 23 to 29, 20 to 22, and they're associated with this later extension. And all of these laccoliths have ore deposits associated with them of some kind. I have a whole presentation on the Pine Valley Mountains, and maybe I'll give that soon here. Okay, so if you understand the Earth's behavior, it's rational if you understand the rules by which it exists. And plate tectonics helps us understand how the Earth behaves. Okay, so if you understand plate tectonics, you can kind of understand why the Earth is behaving the way it does. Okay. So let's look at the depositional history of arches compared to where we are right here. So again, we got 250 miles between us here. So let's look at a stratigraphic column of our area. A stratigraphic column is nothing more than the strata, the layers, in a columnar fashion represented in a graphical format. The Navajo sandstone, we all know what the Navajo sandstone is, right? It's about 2,000 feet thick in our area. Okay, it's a massive aeolian windblown deposit. And all of these little lines here, those are all events, chapters in Earth history. Something different was happening in each one of those little layers. This is Southeast Utah. Okay, this is in the Moab area. Same units, but some things are happening here that are a little bit different. Here's the Navajo. You can see how it thickens toward the west, southwest. This is the Entrada sandstone. I'm going to mention it here because this is the main unit in Moab where all of the arches are within the Entrada sandstone. Okay. So if you look at a cross section through the area, this is just north of Moab. This is Green River right here. This is Diamond Valley, just to the north of us. If you look at the Navajo sandstone, it thickens dramatically from east to west. If you look at the Entrada, it thickens and then thins to almost nothing where we are. In fact, I don't even think it's recognized up in Diamond Valley. So things change laterally in the same time frame. We look at the top of the Triassic, really nothing really happening here. In the Permian, top of the Permian, very similar thicknesses. And then here in our area, we have the Colville limestone at the top of the Pennsylvania, about 305 million years ago. Okay. If you go over to Moab, this is what you see. The Paradox Formation. And the Paradox Formation is about 5,000 to 6,000 feet of evaporites. Does anybody know what evaporites are? Who ate dinner this evening and sprinkled a little salt on there? That's an evaporite. It's halite. Okay. So there are several different types of evaporite minerals that form in the Paradox Basin. So it's different over in the Moab area. And why is it different there? So what we need to do is look at the paleogeography of the area to see why it's different in the area of arches versus this area here. Okay. So about 340 million years ago, Moab's located right in here. This was a very broad, open area of ocean. Very shallow water marine sediments were being deposited at that time. Okay. Nothing really was going on at that time. Right after that, what was happening, the Appalachian Mountains were forming. Africa was slamming into the North American continent. Here's South America. There was an oceanic plate diving down below North America on this side. So this whole area here was under compression. This is the area of the Paradox Basin, very close to the paleoequator. Okay, so it was right in near the equator. So very hot temperature. Good. We're going to be recording still with this one. Okay. Test. Good. All right. All right. So pretty cool map, isn't it? So the Appalachian Mountains were forming from a continent-continent collision on the east side of North America. On the west side, on the west side, you had subduction, or the oceanic plate diving below the North American continent. So that whole area was being scrunched. Okay. Okay.
How many years ago is this?
About 300 million, 305 million approximately.
Thank you.
Sure. So when that happened, we formed this little basin right here. Oh, the battery going out. Right here. And it had an opening to the south. Okay, so seawater was able to get into this little basin right in here. That's the paradox basin. So when you have evaporating seawater, what happens is you have an opening to the ocean, and when that water evaporates down below this level, it gets stranded, and it evaporates even more down below that level. And what happens when you evaporate seawater is there's a sequence of minerals that precipitate out. The first one is calcium carbonate, then you get halite, and you get gypsum, and then you get sylvite. Okay, potassium chloride. That's potash. That's what they call potash. That's the valuable mineral that they're mining in the Moab area. So what happened here is that there were 29 cycles of sea level drop, and that helped deposit 5,000 to 6,000 feet of evaporite minerals in the basin. 29 drops. Now, what caused those drops in sea level? Who said? Someone said glaciers? Yeah, it was. The latest ideas indicate globally there were during the Pennsylvanian time period that there were at least 29. If you're a lumper, it's 29. If you're a splitter, it's 33. So glaciation, when the ice sheets formed, sea level dropped, and it stranded this basin, and evaporation took place down to virtually zero. You have to concentrate seawater 64 times the normal concentration to get sylvite precipitated out. And there are 18 of those 29 layers that have sylvite in them. So there's a significant amount of evaporation going on. So here's this basin with 5,000 to 6,000 feet of evaporites deposited in it. And here's our area right here where the Colville limestone is, right? So that's why the difference between the Paradox Formation here, right, paleogeographically, and then we're right on the carbonate shelf where the Colville limestone was deposited. So that's how you explain why in one part of the state you have evaporites, in another part of the state you have limestones. Make sense? Yeah? Okay. All right. So the Paradox Formation is the oldest rock in Arches National Park. It was deposited in a bay, okay, with an opening to the southeast. 29 cycles of evaporite deposition, and this is actually the precipitation sequence. Now, it doesn't always wind up with sylvite, with potassium at the last gasp of evaporation. And sylvite isn't always preserved. Think about this. When sea level rises, sylvite is very soluble. So if it was present and that new seawater comes in, it's going to dissolve the sylvite. So the fact that we have sylvite preserved at all is pretty amazing. All right. So here's the Paradox Basin. There's a mountain chain, there was a mountain chain just to the northeast of the Paradox Basin. This is a very thick accumulation of sediments, at least 5,000 to 6,000 feet. If you look at a cross section through the basin, this is what it looks like. It's a very simplified cross section. On the shelf, you've got all kinds of shallow water carbonate deposition. There are small reefs, algal mounds, etc. And these are good reservoirs for hydrocarbon exploration. That's what they typically go after. These are conventional traps in the carbonates. Okay. Any questions on that? So let's talk about salt tectonics. It's a very unique mineral, salt. Halite and gypsum have a density of about 2.1 to 2.3 grams per centimeter. Remember that. Sedimentary rocks like sandstone, shale, and limestones they're much more dense. Okay, 2.4 to 2.8. So what happens with salt, when it's subjected to heat and pressure, it starts to mobilize. And because it's less dense, it has a tendency to come up vertically through the section. So we can actually pierce the sediments. You'll hear the term diapir for salt, and that's due to the fact that it will actually pierce more dense sediments as it rises. So because of that, it will tend to mobilize vertically, kind of like a lava lamp. And if you look at the way salt deforms, salt can deform as salt walls, okay, canopies, little rollover anticlines, okay, or piercement domes. There's a lot of ways that salt will deform based on how it's loaded. If I'm roller pinning it from one side, I'm going to develop little anticlines, little synclines, okay, little hills and valleys. If I'm loading it unevenly, like this, okay, if I'm stepping in jello, with deltas, for instance, I'm going to deform it in this fashion here. So the salt actually tells you which way the salt was loaded, what type of system loaded it. Okay, so what's the paradox formation comprised of? I've pretty much talked about that already. But we have calcite precipitating out first, 2 to 3 times the normal concentration, seawater. Then we have gypsum and anhydrite, 3 to 12 times, halite, table salt, and then potash or potassium chloride. That is the evaporation sequence that we see typically in evaporated seawater. So here is this evaporite basin. And what happens after the paradox formation was deposited, it got buried by a very thick bunch of sand and silt and clay called the Cutler group. So it buried the salt, and it buried it in a fashion from one direction. It was a unidirectional pattern parallel to the Uncompahgre uplift. So this is a roller pin. This is one of those roller pin type of deformation sequences that we see. So here's just a sequence of what happened. Here's the Cutler group. Here's the salt. These are some faults in the basement. And what happens when this is roller pinned out is that the salt comes in contact with these faults. And because it's being pushed in this direction, it comes up against these buttresses. It has a tendency to rise vertically. Okay. And you wind up with large salt columns, ridges that are parallel to the Uncompahgre uplift. And that's what they look like. Okay, so this was the uplift that was shedding all of that material on top of the salt, and it roller pinned it out to the southwest. So that's why those walls are parallel to the uplift. And they formed in response to that progradation of the material from the Uncompahgre uplift. And it's localized. It started to come up to the surface because of the faults that were buried deeply. This is a model. It's actually, it's a proprietary model. It's comprised of silicone and clay. And there are artificial buttresses that were put in here that are supposed to replicate faults. And it's going to be loaded evenly from the right-hand side, and it's going to show you how the deformation would look in real salt. This is what it would look like. So you start to see the roller pinning, the early deformation on the right side, and then gradually with time, you start to see the development of later formed. And then you see a buttress here that was a fault, and you can see the material spilling out onto the surface. So the salt actually came up onto the surface. This is just a laboratory simulation. Pretty cool, huh? All right. So this is a cross section across a portion of the Paradox Basin. Okay, let's see. Here are the Abajo Mountains. Here are the, let's see, I'm trying to find Moab here. I can't see it. I should have labeled it. Here's Blanding. There's Moab right here. Okay, so this is coming right across a portion of the park. And this is what it looks like. Okay, we've got a basement here. That's the Uncompahgre uplift. Here are the basement faults, right? And then here's the Cutler group sitting on top of it. And the salt was deformed and it came up to the surface. Okay, due to that roller pinning. This is what it looks like in outcrop, actually on the surface. This is the Onion Creek diapier. This is the Paradox Formation cap rock exposed at the surface. So this salt actually came up to the surface and is exposed present day. And that's a geologic cross section through it, just to show you this is the paradox coming up to the surface. Okay. So this is not an uncommon occurrence, having salt basins. This is the Gulf of Mexico around 160 million years ago. This is a restricted basin close to the paleoequator. during entrata time. The Luan salt was deposited in this basin. It's about the same thickness, 5,000 to 6,000 feet. And this is a seismic line across the area. And this is all salt, deformed, coming up to the surfaces, salt domes and canopies and rollers. Pretty cool. Okay. How arches form. I'm going to spend a lot of time on this particular topic as well. Any questions about salt tectonics? Okay, we'll get more into it in the salt mining as well. Okay, how arches form. So there's a very good article by Grant Willis in 2009 in the Utah Geologic Survey notes. He just had a few points that I like to use to just address why arches and how arches form. So there are some requirements for arches to form. One is that you have to have a very thick, homogeneous rock. All of the rocks, all of the arches in Utah are comprised of rocks that are almost entirely quartz. So they actually act like a single crystal of quartz. And if you look at a quartz crystal, a large crystal of quartz, what you can see is this arcuate pattern. This is called a conchoidal fracture. That is how quartz fractures naturally, okay, as a conchoidal fracture. Who shot a BB at a piece of glass? Anybody? Yeah, you get a round, that's a conchoidal fracture due to a pinpoint of stress. Okay. It needs to be moderately strong or brittle, high erosion rates, high incision rates to create deep canyons. Big arches need big cliffs. I agree. Near vertical, subparallel spaced joints, like what we see here. Okay. Weaknesses, in or below the homogeneous rock that act as seed sites. This is something I'm gonna probably elaborate on a little bit more as we go on through the talk, because it's a critical element in how these arches form. And you'll see in a few minutes what I mean. So the Entrada sandstone is where almost all of the arches in Arches National Park are forming in. It's about 200 feet thick. It's almost entirely quartz. It's extremely homogeneous, fine-grained quartz sandstone. Ideal for arch formation. It's about 160 million years old. It was deposited as sand dunes, and it's very homogeneous. Okay, this is a video from Arches National Park. It's a really good summary on how arches form and a little bit about salt tectonics and the tectonic history. What you're going to see in here, in one portion of it, is that the tectonic history, the zone of the time of compression, actually impacted the salt in eastern Utah, and I'll try to point that out to you during the video. So I'm going to play this now.
Over 300 million years ago, our Earth's surface was very different. The land masses were drifting, colliding, and transforming. As tectonic forces pushed and pulled what was to become North America, the ancestral Rocky Mountains rose. To the west of these mountains, faulting and subsidence created the Paradox Basin. Over the next 15 million years, changing sea levels filled the basin 29 times. Each time the oceans receded, salt water became trapped in the basin. The trapped water evaporated, leaving a massive deposit of salt over 5,000 feet thick. As time passed, the mountain range eroded. Vast amounts of sand, rock, and debris accumulated on top of the salt layer. Under this tremendous pressure, the softer salt beds were forced westward. When the salt encountered deep faults, it was blocked and forced upwards. Over the next 75 million years, an enormous salt wall, 2 miles high, 3 miles wide, and over 70 miles long was created. Eventually, the salt stopped flowing, and a mile-thick layer of rock was deposited over it. Then, some 60 to 70 million years ago, tectonic forces caused some of the deeper rock to bend, forming a dome.
That's the compressional episode.
Long parallel cracks called joints formed in this bent rock. Later, when the Colorado Plateau rose, the Colorado River and its tributaries eroded away most of this mile-thick layer of stone. When the cracks became exposed at the surface, water seeped through the joints, allowing some of the salt to dissolve. With this salt removed, the unsupported stone collapsed over time, creating Salt Valley. At the edges of Salt Valley, some of the remaining fractured rock layers continue to erode, forming thin sandstone walls called fins. These fins were slowly worn down, and sand collected between the closely spaced vertical walls. Slightly acidic rainwater combined with carbon dioxide in the air, forming carbonic acid in this trapped sand. Over time, the acid dissolved the calcium carbonate that held the sandstone together, slowly wearing away the rock until openings were formed. In other fins, an exposed layer of weaker rock lay beneath the stronger one. The weaker stone weathered first, undercutting the upper layers and creating a hole. In both cases, the weight of the overlying rock caused fracturing above the opening. Eventually, gravity pulled the loosened stone away, creating the distinctive natural arch formations. Water and time continue their relentless sculpting of this landscape, creating and transforming the natural wonders of Arches National Park.
I couldn't have said that better myself. It's a really good illustration of how the Salt Valley's formed out there and how the edges are where a lot of the arches are because of the fracturing along the edge of the valley. So this is just a map of, any questions about the video? You saw that compressional event. That was the compressional event that we witnessed here that formed all the folding. Only over in the eastern part of the state in the Paradox Basin, it was buffered by the salt. So it wasn't quite as active, but it did impact the area. And we know that the extension did because of the LaSalle Mountains. Okay, so we know as you come into the entrance of Arches National Park, which is right here, there are a number of places that you'll pass. This is the windows area, which is famous. Here's Balance Rock, Fiery Furnace, landscape arches up here. You see a lot of different arches along this edge right here in Salt Valley. So that's Salt Valley, and this is Moab Valley. The Main Street in Moab is sitting in the middle of that syncline. Okay, so that's where all the salt dissolved, and you're able to pave a main street through there. So if look at a cross section through the Salt Valley down through the Moab Valley, this is what it looks like. So the underpinning of both valleys is a very large salt anticline, what they call an anticline, two of them. And all of these fractures right here, that's what you see all along this edge of the valley, okay? And that's why you have a lot of arches there, because of the fracturing due to the collapse of that valley, the Salt Valley. This is what it looks like from the air. This is Devil's Garden from the air. That's the loop right there. That's the trailhead. And that's what it looks like from the ground. So lots of fractures and potential for arch formation in the entrada. If you look at right here, this is the Moab Fault at the Visitor Center. If you look across Highway 191, you can see all the faulting in here. Everybody see that? All the offset? That's the part of the Moab Fault. So you get to see a lot of cool geology just from the Visitor Center. It's beautiful if you haven't been there. Okay, so now we're back to this question right here. How do you get seed sites? What is the actual mechanism to create those seed sites? So let's talk about that. So we all know that geology is an observational science. We gather observations and we utilize as little math as possible, but rely heavily on geology, biology, physics, and chemistry, right? And we convolve those into interpretations. But most of our time is spent gathering observations, okay? So one thing I didn't mention, okay, yeah, it's pretty simple usually. Let's make some observations. Anybody care to make an observation? Not interpretation, just an observation. Birds, okay. Anything else? A stake in the ground, yeah. Some of the trees are bifurcated and some are not, right? Well, it's really not a whole lot more than that, right? So we don't have too many observations, so I'll give you the interpretation. Buried power line, right? Right, pretty bad, I know. All right. One thing I didn't mention to you is that Crystal and myself have, we used to work for Road Scholar, and we calculated it out today. We probably spent at least 250 hours in Arches National Park over the years together. And then I was doing my thing and she did her thing off alone. So a lot of time was spent in Arches National Park. So we've had a chance to digest the geology and make some observations and interpretations. So let's talk a little bit more detail about the Entrada and the underlying formation, which may provide answers to what the seed sites might be. So the Entrada formation is underlain by the Carmel formation, which is split into the Dewey Bridge and the Page Sandstone. And in the area of Arches, it's called Dewey Bridge. If you go to the west, if you travel through Escalante, you can see the Page Sandstone. If you go to Carmel Junction, Mount Carmel Junction, it's the Carmel Limestone. Shallow ocean, and here are the environments of deposition: tidal flat, small streams, and shallow sea. So that's the transition from when you go from Moab over to the west, you go from tidal flat, small streams into shallow seas. The Entrada was deposited as coastal sand dunes. Okay. So let's take another look here. So there's an exposure coming into Dead Horse Point right here, sitting right here. So you come down Highway 91 or come up Highway 91, you take a left or a right on Highway 313. And this exposure right here is a great exposure of the Entrada and the Dewey Bridge. The Dewey Bridge, what's your first impression of this formation, of this member? What does it look like? Yeah, it's crinkle cut fries almost. Yeah. So here's the boundary between the two. So here's the windblown Entrada sitting on top of Dewey Bridge tidal flats. And you can see the deformation. You can kind of trace things around a little bit. It doesn't go very far. So something happened to deform the Dewey Bridge. What happened to the Dewey Bridge? Let's see. So here again, we've got the Dewey Bridge, and then it's deformed, but why? Why did it get deformed? That's the big question. So an article appeared in Geology, July of 1998. It was a great article. I mean, I get goosebumps thinking about this article, right? And they had 6 explanations for the deformation. The first was compression related to plate movement. Remember that early compression we talked about, right? The second was sliding of soft sediments down a paleo slope. Maybe that did it. Dissolution of evaporites in the tidal flats. Sometimes in tidal flats we get evaporites, and if they dissolve due to rainfall or due to sea level rise, you can dissolve them and the sediment gets deformed. And that was what their explanation was. One person said, 2 people said that it was due to loading of the Entrada on top of the waterlogged tidal flat sediments. Another person said it was liquefaction due to earthquake activity. Interesting. Then the authors of the article said that it was deformation caused by a meteorite impact. And that was their primary purpose of this article, was to explain the impact, and that caused the deformation. So I don't think that's what it was. I don't think that's what it was. And they talk about Upheaval Dome. Everybody been to Upheaval Dome? Yeah. Anybody hike down into it? Yeah. Have you sampled the sediments down in there? If you go down, next time you do, if you can, take a sample back home and put it in some water and see what happens. Dissolves pretty rapidly. So anyway, I'm not going to give that away. So this is what it looks like. This has been described as a big controversy about what Upheaval Dome is. Some people say that it's a salt intrusion, and some people say that it's a meteorite impact. The reason they say it's a meteorite impact primarily is because they found some shocked quartz grains in it. Just a few grains of quartz that appeared to be shattered, and they explain that to be due to meteorite impact. Okay, in the oil business, there's a very commonly used tool. It's been used for over 100 years called gravity. Now, salt is less dense than the surrounding sediment, so it has less of a gravity expression. So gravity should pick up salt quite easily. And if you look at a profile across a salt dome, this is what it looks like. It has a lower gravity response because it's lower density material. And what we like, but in the oil industry, what we like to do is explore for these, because along the flanks of those salt domes, you find traps for hydrocarbons. So it's a well-known tool. We use it all the time for a lot of other things as well. So in this case, if you look at the salt in the Moab Valley and Salt Valley, you can see all of the, in Paradox Valley, here's Moab Valley, here's Salt Valley. You can see the expression of the salt all along those valleys on the gravity map very clearly. And if you go over to, and that basically is showing the linear ridges that were rolled out in front of the Uncompahgre uplift. If you look at the gravity expression over by Upheaval Dome, we also have a gravity expression there. So high confidence that it's salt and not a meteorite impact, okay? All right, okay. So I'm gonna diminish this idea here about it being an impact crater. We're gonna come back to that outcrop again. We're gonna look a little bit more closely at this outcrop. And what you see, just make some observations, is that you can see the thickness here. You can see a couple of marker beds. You can trace them around, and then you see a thickening. Everybody see that? Yeah, that's pretty cool. Yeah. How the heck did that happen? And then you come over here, and here's the boundary again, Dewey Bridge. This feature right here. Everybody see that? Right there. That is a fluid escape structure. That's what happens when you have liquefaction. When you have shaking, in waterlogged sand, which in the Dewey Bridge, those tidal flats, you shake it and the water tries to escape. And when it does, it drags the sediment up to the surface. And that's what happened here. And they've been reported everywhere in the Dewey Bridge where it's deformed like this. So I've got thickening into Dewey Bridge thins, and I've got fluid escape. So the observations are thickening, again, into the Dewey soft sediment. SSD is soft sediment deformation, and indications of fluid escape. Okay, so here I have tidal flat material being overlain by coastal sand dunes. And when you do that, you get progradation of the sand, and it's loading those waterlogged sediments, right? So maybe that one of those explanations of loading of the entrata might be correct. So again, so the way I'm going to interpret this is the Dewey Age, we had Dewey Age earthquake activity that created the soft sediment deformation that you observe here. And the entrata infilled that post-earthquake deformation. Okay, so during Dewey time, you had some shaking, and it shook up those waterlogged sediments. It made all kinds of crinkles and folds in them, and then the Dewey dunes migrated over and filled in that topography created by the soft sediment deformation. What does that have to do with anything? We'll show you. Okay, so when I look at all these explanations, and you can attach some credibility to some of them, and I think this is probably a good one. Liquefaction due to earthquake activity, maybe some entrata loading, okay, of those waterlogged sediments, and maybe this. But there's also another explanation that was proposed by Kark in 2024. You all know who Kark is, right? Sedimentary infill of the Dewey earthquake deformation. Now, I'll show you why that's important in just a second. Okay. So let's look at those seed sites. How do you form those seed sites? Well, you know, when I was thinking about this, a lot of times when I do this, I have it in my office. I'll sing. I'll kind of sing some songs, and you know, the song I was singing the other day was I'm a Believer by the Monkees. You all familiar with that? I'm a Believer. Now I kind of assumed that I sang well because whenever I'm at a concert or at a birthday party, you know, people kind of turn around and look at me, you know. So I just assumed that I'm a pretty good singer. So I'm sitting in there and I'm working on this, and my wife, Crystal, says, "Mark, would you please stop? You please stop." And I said, I thought she was joking. So I got up from my chair and I looked, and then I saw her face. Oh, all right, okay. So it's you can leave now if you like. All right. I'm sorry. All right. You get it now? No? Okay. I'm a Believer. Okay, so boy, the colors are projecting strange on there. Okay, so here's the deformation in the Dewey Bridge, and here are those Entrada dunes migrating out and filling in the topography within the Dewey. Okay, so you can see the thickening into the Dewey. That's what we see in outcrop. And then what happens is you have some rain, and slightly acidic rainwater seeps down into the Entrada. And because the Dewey Bridge is not that porous and permeable, what happens is the water kind of settles down into these low spots. So that slightly acidic water gets to sit there for quite a while. And then what happens is that it allows for dissolution of the Entrada. And that creates zones of weakness at the base of the Entrada, and it creates the seed sites for arch formation. Okay, makes sense? Okay. So here's an arch, turret arch. You've all seen turret arch. It's really hard to say because there's a lot of erosion in here if the Entrada is thickening down in there. But what I do see is a Dewey Bridge coming down into a fold, into a little gully there. Don't know if that's really happening there or not. Here's another, is it questionable? Here's a marker bed that you can trace through there. Really can't tell if the Entrada is thickening down into that, but you can look back here and you can kind of see some thickening in the overlying Entrada, but you're really not sure if that's really thickening or not. So it's a hypothesis that that needs to be tested. Okay. So as far as this goes, I think we might have a proposal or a hypothesis to demonstrate how those seed sites form for arch formation. And I may be very alone on this, kind of like adult children of normal parents annual convention, you know. So we'll see. Maybe this idea will get out there and people will test it and see. Okay. Everybody okay? No, okay, good. All right, salt mining. Let's talk about that. Okay, we're going to look at this area right here around Dead Horse Point because it gives you a good vantage point. Dead Horse Point, let's see, here's Moab right here. Here's Dead Horse Point, and you can see these little white irregular shapes. Those are evaporite ponds. Here's Upheaval Dome sitting right here. This is what they look like in a little zoomed in. They add blue dye. What did I do? They add blue dye because blue dye enables faster rates of evaporation. And I'll explain why that's important in just a minute. So when you drive into Dead Horse Point, what you'll see is a feature called the Cane Creek Anticline. And a view from Dead Horse Point looking in this direction looks like this. Everybody see this large feature here? That is the Cane Creek Anticline, and that is a salt pillow, okay? And that's why they mine the salt there, because it's shallower, because it's about 2,000, the top of the salt is about 2,000 feet below the surface. They used to mine with a shaft mine operation back in the 1920s out here, but they had an explosion in the mine, and they have a different technique that I'll elaborate on in a second. So that's all salt. And this is what they're doing. There are two zones that's called the Sylvite number 5 and Sylvite number 9. This is the shallowest one. It's only 12 feet thick. They pump salt water down there. They dissolve the sylvite and they bring it out onto those evaporation ponds, add the blue dye, evaporate it, and then they scoop it up with big payloaders and process it. And that's the mineral sylvite, KCl, potassium chloride. Gypsum and anhydrite, basically gypsum is used for sheetrock, halite, table salt, ice removal, right? And potash is used for fertilizer, water softening, salt substitutes, you name it. The reason they like potash salt is because it's the most expensive and most rare salt, and it goes for about $290 a ton right now on the open market. Okay. Talk about petroleum occurrence. So when you drive into Dead Horse, what you'll notice are all these little green blobs. Those are all oil fields. Okay, and when you go out there, what you'll find are little operations like this with a tank and a little pump jack. So they're pumping oil out of a very relatively thick layer, and I'll talk more about that in a sec. So where does it come from? Well, in an evaporite basin, what typically happens in any one evaporite cycle is that you get salinity stratification. You have relatively normal seawater up at the surface, and then it gets more and more dense as you go down to the bottom. And salt crystals actually precipitate out of the water and they settle down there, and it becomes a very oxygen-starved environment. So any plankton that's living up in this surface water environment, that's either zooplankton or phytoplankton, when it dies, settles down into this anoxic environment, and you deposit very high total organic carbon source rocks. Okay, does that make sense? Okay, so we have source rocks being deposited. So when you look at this particular illustration of salt, it's really very simplified. So when you look at core data from the USGS, this is actually what it looks like. Many cycles, and you have these dark layers. This is the Cane Creek Shale. It's very rich in organic matter. It is the source of the oil up on the shelf. So what happens is that shale right there gets buried under more intense pressure and temperature. Salt is an excellent conductor of heat. So that salt is extremely warm. So the heat alone and the pressure will actually mature that organic matter into petroleum. And the oil migrates up dip into these reservoirs up on the shelf that I mentioned before. These are called algal reefs. And the genus of the algae is Ivanovia, just so you know. And those are called conventional reservoirs. That's what typical hydrocarbon exploration goes after, conventional reservoirs. So you have a porous rock, hydrocarbons migrate into a trap, you drill a well into it, and you produce it. That's typical conventional exploration. This is not typical, okay? This is unconventional hydrocarbon accumulations, okay, out there. And what we have here is the source rocks being caught up in a salt anticline. And what happens is the oil actually migrates into fractures within the anticline, and those fractures are pursued by the drillers. So they'll drill down and they'll drill perpendicular to as many of these fractures as they can, hook them up, and produce from those fractures within those organic rich rocks. So that's what they're doing out there at Dead Horse Point.
No fracking out there?
They do frack. There's no reservoirs, aquifers out there, so there's no danger of anything out there. That's a good place to frack. If you're going to frack anywhere, frack around Dead Horse. How are we doing? Good? Good. I know that's a lot. Thank you for following me into the mud. But we're about to emerge. We don't have much more to go. So we've gone through the plate tectonic history, the depositional history, paleogeographic foundation, salt tectonics, how arches form, salt mining, and petroleum occurrence, all in one evening, within an hour, I think. Yeah. Okay, we're doing good on time. I told my wife we'd be out of here in an hour. Okay. So with that, wait, there's more. There's just a little bit more. Okay, when you go into Arches, you go all the way out to Devil's Garden, the Devil's Garden area. There's a place that you can park, and we're going to look at Landscape Arch. It's a very easy hike. I recommend it, highly recommend it. It's about a little under 2 miles, very easy to get to. It's the largest arch in the world. There are larger bridges, natural bridges, but this is the largest arch in the world that we know of. So it's important for you to see it. Anybody who's been out there to see it? Yeah. Right here, this is about 6 feet. That's how thick that is right there. So how much longer do you think it's going to be there? Yeah. So back in 1991, there was a gentleman by the name of Michael Mueller. And he was out there hiking. And at that time, you could hike under the arch and look back toward Devil's Garden. They don't allow you to do that anymore. You know, there's a reason for that. So what happened there is that there was a collapse. That was a 73-foot long slab. Okay. That's why there's only 6 feet left here, approximately.
I really don't want to walk under that.
There were 2 more slabs that fell. One was 47 feet and one was 30 feet across back in 1995 as well. So if there's one thing that I'd like to get across to you tonight is visit Arches National Park, because you just don't know when those guys are going to be gone. So with that, I'm going to say fini. That's the end of the presentation. And if you have any questions, you can reach me at carquest@gmail.com. Okay. That's a real email address. I made it up today. Hey. I know that was a lot. It was a lot. I mean, you know, a lot of those topics I didn't need to cover, but I just wanted, next time you visit Arches National Park, I want you to have a little bit more information, make it a little bit more interesting for you. When you go to Dead Horse, you go to Upheaval Dome, Canyonlands, that whole area. It's spectacular. And if you get a chance, go down the Schaefer Trail. Also, that brings you in behind all those evaporative ponds, so you can see the operations there. It's pretty cool. Any questions? Any answers? No questions? Yes.
So when you go down to George's restaurant downtown, they have this historical photos of the old oil wells
Yeah.
in Washington County. What happened to the oil? Was that all played out, or was it not economic?
Yeah, it wasn't economic. A lot of them were dry holes as well. There are some oil accumulations in Virgin. There's actually some seepage in the Navajo, both out on the Arizona Strip, where pioneers used to use the grease to on their wagon wheels. And there are other places where there's actually seepage. The problem with oil exploration here is that the source rocks are not buried deep enough to mature and expel a significant amount of liquids. That's the problem right here. The uplift of the Colorado Plateau actually stopped the maturation process. So the rocks had to be continuously buried deep enough to go through the oil window and maybe gas window. But what happened here is that because of the uplift of the Colorado Plateau, the maturation was stalled and we didn't get as much oil. Yes, sir. Oh, hey, Les.
Would you say Johnson's Arch was formed the same manner as the arches?
Yeah, Johnson's Arch, you all familiar with it? Familiar with Johnson's? Yeah, the weak point there, it's a massive sandstone. It's got a lot of fractures, and it's a valid arch. I mean, it's not a blind arch. You can see through it, so it's a real arch. At the base of that arch is the Kayenta Formation. The Kayenta Formation weathers faster than the overlying Navajo, so that forms the seed site for the arch at Johnson's. So it formed the same way. Yep. Not with the same deformation like the Dewey Bridge, But what you see there is there was differential erosion that created a weak point. The seed site is merely a weak point. How you get it, they're going to be different ways of getting that. So yeah. All right, silence. Either I did a really good job or it just took too long. So, okay. No other questions? What about, what'd you think about the Dewey Bridge? It's pretty fascinating. Not many people concentrate on that, but we've made a lot of observations in it. You can actually see similar features in the Dewey is just above the Navajo sandstone. Does anybody see the white pocket talk I gave? The Navajo? Yeah, the Navajo out there, just below the Dewey Bridge, was subjected to an extreme amount of shaking. So it's not unreasonable that the unit directly over the Navajo would be also subjected to shaking as well during earthquake activity. And during that time, what was happening on the West Coast is you had an extreme amount of earthquake activity due to subduction on the west side of the continent. Okay, so I think earthquake activity, infill of the Entrada, maybe dissolution of some evaporites, that might have fit the observations that we see out there. Yeah. Well, you guys have been a great audience. A little shallow and insincere, but great nonetheless. Thank you for coming tonight. I enjoyed having you. Hey.
The